Hello there everyone, and welcome to lecture 10. So what we'll be doing in this lecture is we'll be looking at the rules for our natural deduction system for first order logic, so FOL. And in particular, what we're going to be doing is looking through all of the rules. So this actually won't take very long, and that's because most of the rules that we're going to use will be ones that we've already talked about. So, just as a spoiler, every TFL rule is also a rule for FOL. In fact, all we're really going to do is we're just going to add a few rules that have to do with more operators. The operators that are specific to first order logic. So what we're going to have is we're going to have an introduction and elimination rule for a universal quantifier, an introduction and elimination rule for an existential quantifier. We'll have some rules that let us convert certain quantifier phrases into other ones. And then finally, we're going to have introduction and elimination rules for the identity predicate. So what we'll do in this lecture is talk through each one of these, try and explain them, give a little instance of them, and then basically set us up to be able to do first order natural deduction. So cool, let's get started. So as I said just a second ago, the most important thing to note is that our natural deduction system for first order logic includes all the rules that we learned for TFL. Similarly, all of the proof theoretic notions we defined for natural deduction in TFL also apply here. We'll talk a little bit more about them in the next lecture, but it's helpful to know that everything we've done over the past 2 lectures will also apply for a natural deduction in FOL. And all we're really going to do is add a few more rules to deal specifically with the new operators that FOL introduces. So let's start with probably our easiest one, which is universal elimination. So universal elimination is a rule that we can apply to a sentence whose main operator is a universal quantifier. And the idea behind it is fairly straightforward. It's that, look, if we know that everything is F, you can then rightly infer that any particular thing you like is F. So in slightly more formal terms, right, if you have a sentence of this form that has a universal quantifier as its main operator, you can replace any of the relevant quantified variables, any of the relevant bound variables, with whatever name you like, and you'll still get a sentence that's true. Note, importantly here, you have to replace every occurrence of the relevant bound variable with the same name. But of course, it's still going to be true, right? Because one, we know that if you're using this name, it's going to pick out something in the domain. We don't necessarily know what it is, but we know it's going to pick out something in the domain. And of course, if this is true, if literally everything satisfies this, which it must be if it's on a proof line, then whatever name we pick out must also do it too. So that's the idea of universal elimination. Right? From a sentence of this form, with a universal quantifier in front, you can derive a sentence replacing the variables with any name you like. So that's universal elimination. Unfortunately, universal introduction is slightly harder. So the idea behind universal introduction is you might think, right, what we might do is, well, if we could establish that every possible substitution instance makes some sentence true, then we can infer the universal. That is, right, if we could show that A's an F, and B's an F, and C's an F, and D's an F, and E's an F, and so on and so on and so on for every possible name, then we could infer everything's an F. Of course, the problem is we can't do this with every possible name because there's an infinite number of possible names. So we can't just simply kind of brute force our way into introducing a universal quantifier. So what we're going to do instead isn't think about every possible name, but we're going to pull a trick that we did a little bit earlier when we thought about interpretations, and we're going to think about arbitrary names. So our idea is going to be that if we can show that a relevant sentence holds for some arbitrary name, that is, some name that picks out any object you like in the domain. It's literally arbitrary. It's completely up for grabs as to what object it's picking out. But if we use an arbitrary name like that, and it makes a relevant sentence true, then we'll know that the universal quantification is true. And the reason why is because the arbitrary name effectively stands for any name at all. Again, the key idea is that it's arbitrary. It's literally just sort of, yeah, we could pick any of them we like. And that's sort of what the arbitrary name is standing for. So that's the kind of motivation. Now here's the rule as it's written. The idea is if we have a sentence like this, where we have a particular name occurring, right, and this name hasn't occurred in any undischarged assumption, and the variable that we want to use does not occur in this sentence, then what we can do is we can replace every occurrence of the arbitrary name with a particular variable that's bound by our universal quantifier. Now note, every instance of the name needs to be replaced with a variable. You can't pick and choose. So again, the thought here is that, well look, if C, in this example, is literally just arbitrary, that is, it doesn't stand for any particular thing, it kind of stands in some ways for every object in the domain, or better, any object in the domain, and it makes our sentence true, then that's going to be the case for every object. So if we can have an arbitrary name plugged in here, then cool, we can replace it with this universal. Now the thing to note when we use our universal introduction is it always delivers a sentence with a universal as its main operator. We have restrictions on when we can apply it. Again, the important things to note, the restrictions here, the name that we're going to replace can't occur in any undischarged assumptions. So, for example, you could never do universal introduction if the sentence you wanted to use here was one of your starting assumptions, because you never discharge those. Right? So, C can't be in an undischarged assumption, and the variable that we want to attach here can't occur in this sentence. Now our second one here basically just prevents us from having a clash of variables. That's what our second restriction does. And our first restriction makes sure that the name C that we're playing with here is arbitrary. It's not naming some particular individual or some particular entity in our domain. So there we go. We've had universal elimination, which basically is, hey, if we know the universal is true, then we can derive any instance we like. And we have universal introduction, which is if we have an arbitrary instance, then we can derive the universal. So that's our first pair. Our second pair have to do with the existential quantifier. So our first rule here will be existential introduction. An existential introduction, thankfully, is extremely easy. The idea here is that if we know that some particular thing A is F, then you know that something's F, because A is something, so there's got to be at least one thing in the domain that's an F. So slightly more formally, our rule here is that if we have a sentence of some form, featuring a name, we can replace that name with a bound variable attached to an existential quantifier. The only restriction we have here is that the variable we replace the name with must not already occur. And this really is just to, again, ensure we don't have anything like a clash of variables. Now what's kind of neat is because the existential is so flexible, you can actually replace some or all of the instances of a relevant name. So for example, if you had TCC somewhere on your proof line, then you could derive 3 different sentences from it. You could derive this sentence, which replaces just the first occurrence of C, or you could derive this sentence, which replaces just the second occurrence of C, or you could derive this sentence, which replaces both occurrences of C. All 3 of these were equally good derivations. All would be good sentences you could derive using existential introduction from this sentence already. So again, existential introduction, the basic idea, right, is if you know that some particular thing satisfies a sentence, then you know something satisfies a sentence. So you can go from featuring names, a sentence featuring names, to a sentence with an existential as its main operator, where you've replaced at least some of the names with a relevant variable. So that's existential introduction. Unfortunately, existential elimination is difficult. So to kind of get the idea for existential elimination, it's helpful to remind ourselves that existentials are a lot like disjunctions. They're a lot like disjunctions in the sense that they're easy to make true, but they're hard to know what we can derive from them. So if we know that something's an F, well, we know that there's going to be something in the domain that's an F, but what we don't know is which thing it is. However, we can use a trick here. And our trick that we're going to use is we'll again appeal to arbitrary names. So appealing to arbitrary names is going to help us out. So the basic idea when we do an existential elimination is we're going to replace the bound variable with an arbitrary name. That is, again, a name that can literally stand for anything in the domain. And then we're going to see what we can derive. And if we can derive something useful, we can then eliminate our existential to get out what it is we want. So here's the rule. Basically, if we have a sentence that features an existential as its main operator, what we can do is open up a subproof that starts with a substitution instance of that sentence, where we replace the variables with some arbitrary name. Then, within the subproof, we derive some result. Now, importantly, there are some restrictions here. But once we derive this result, we can then close this subproof and move this very same result one line to the left. And this will be derived then from eliminating the existential that we started with. So we cite our existential and the subproof that features the arbitrary substitution instance. Now, here are the restrictions. Our first restriction is that the name we use here in our substitution instance must not occur in any undischarged assumption before we start the subproof. So what this kind of guarantees is it helps to guarantee that C is an arbitrary name. That is, it's a name for any object in the domain, not some particular one. Similarly, our second restriction is that the name C must not already occur in the sentence that we're using. That is, we can't have a sentence that already features the name we want to use in our substitution instance, because if it does, it's not arbitrary. We already know something about it. So again, these first two restrictions guarantee arbitrariness. Now our last restriction is that, again, the name that we're talking about, C, cannot appear in the result that we're going to get out from the elimination. Now, this again ensures that everything we did in here was never talking about any particular or specific object. It was about some particular thing, but we don't know which. Right? Again, it's always just about an arbitrary object, an arbitrary name. And we're guaranteeing this by making sure that our name C doesn't crop up anywhere beforehand. It doesn't appear in this sentence, and it's not going to appear, or it doesn't appear in the result we get out. That's the kind of key idea when we do existential elimination. So again, the idea is we start with an existential, we do some arbitrary replacement, we derive a result from this, and then that is the thing that we're going to derive from the existential. Now here's the parallel, if you like, with disjunction. So think about what we do with disjunction elimination. Disjunction elimination, we have a disjunction and we say, look, we don't really know exactly what's going to follow from it, but if we can start with this disjunct and get to this result, and start with this disjunct and get to this result, then we know no matter which way the disjunction is true, this is going to follow. In effect, what we're doing here is the same thing. We're saying, hey, we've got this existential, and it tells us there's something in the domain that satisfies our sentence. And our subproof effectively saying, hey, cool, let's introduce a name. We'll call it, I don't know, Steve, right? And let's just stipulate that Steve picks out the thing that satisfies this sentence. We don't know anything about Steve, other than the fact that Steve is the thing that makes this sentence true. Well, hey, from the fact that we know Steve makes this sentence true, we can derive this other thing. And note, this is going to be the case if we make Steve this object, or that object, or that object, or that object. It doesn't matter. We're always going to get to this result. So cool. This is very much like what we did with disjunction. If Steve's this one, we get to here. If Steve's this one, we get to here. If Steve's this one, we get to here. So really, no matter what object Steve is, we always get to this result. So this is why it's helpful to think about existential elimination as paralleling disjunction elimination. And in fact, if we really think about the nature of the quantifiers, this nicely parallels something we talked about way back when we first introduced them. The quantifiers are very similar to specific connectives. That is, universal quantification is very similar to conjunction. If we know that everything is an F, that's basically equivalent to A is an F, and B is an F, and C is an F, and so on and so on and so on. Meanwhile, if we know that something's an F, that's effectively equivalent to A's an F, or B's an F, or C's an F, or and so on and so on and so on. And in effect, the natural deduction rules we're using for these operators kind of parallel the natural deduction rules we use for conjunction on the one hand and disjunction on the other. So good. Okay. So that's kind of introducing our universal introduction and elimination, as well as existential introduction and existential elimination. It's still kind of helpful to get a grip on existential elimination, because it can come across as slightly strange the first time. So let's think about a case. Suppose we know that something's F, and that every F is G. Right? So we know something's an F, and we know that everything that is an F is G. Well, since something's an F, there must be some particular thing that is an F. Now the problem, of course, is we don't know much about it. We don't know which one it is. We don't really know what it is. We know it's going to be in the domain, but we don't know much else about it. So what we can do, if we still want to talk about it, is we can introduce an arbitrary name. So again, we can use Steve. Right? So let's just call our thing Steve to pick out the object that we know is in our domain that is an F. Now once we have this name, this sort of arbitrary name, and again, all we know about Steve is it picks out something that's an F. We don't know really much else about him, her, it, them, whatever. But we do know that Steve is an F. Why? Because that's the only thing we know about Steve. We don't know which particular object he, she, it, they are, but we do know that Steve's an F because we introduced this name specifically to pick out the thing that is an F. Now what's neat is if we know that Steve is an F, and again, Steve here being an arbitrary name, and since we know that everything that's an F is a G, we can then derive that Steve is a G. And of course, if we know that Steve is a G, we can then derive that something is a G. Because remember, if we know that some particular object is a G, then it definitely follows that there's something that's a G. So we can do this whole chain of reasoning, and here's the neat thing. Nothing in this chain of reasoning depends on which particular thing Steve is. Steve is arbitrary. That is, Steve could literally be any object at all in our domain. There's no particular thing that this name picks out. But we can still use the name to perform the kind of reasoning that we just did here. And this is the kind of key idea behind using something like an arbitrary name. Because Steve is arbitrary, because this name is arbitrary, it could theoretically apply to any object that we're talking about in our domain. Then the reasoning we have here is completely general. It's not dependent upon any particular object, and in that sense, it is generalizable. So this is why the tricks we used earlier with regards to appealing to things like an arbitrary name always work. So when we talk about arbitrary, what it means is it literally it could pick out any object. And because it could pick out any, we can effectively treat it as picking out all. So we can formalize the reasoning that we just did here in the following way. So again, let's suppose we know that something's f, and we know that everything that's an f is a g. Well, what we can do, if we want to derive that there is something that's a g, is we can eliminate this existential. And we'll do this by providing a substitution instance for our existential, introducing some arbitrary name, and in this case we just used A. So A could pick out any object in the domain. All we know about it is that A is an F. That's all we really care. We don't care anything else about it. A is some arbitrary name we've introduced as a substitution instance for our existential because we want to get out some result. So we introduce A, and of course, right, if A is an F, well, we can use A here, so we can eliminate this universal and substitute A in place of our variables, and get if FA, then GA. And cool, now we've got this conditional and the antecedent, so we can derive the consequent. This should be a G, this shouldn't be an F. So, right, we can now get GA, and what we can do now is we can do existential introduction, and we should get, there exists an X, and there should be, again, a GX through existential introduction. And now we have a sentence that does not feature our arbitrary name, and we can take this sentence and export it back out using existential elimination, close our subproof, discard our arbitrary name, and get out something that we know must follow from this existential. And we've shown it follows from this existential by using our arbitrary name. That is a name that literally could stand for any object in the domain whatsoever. So here's a nice instance where we bring together a bunch of the rules we just used. Right? Our whole overarching structure here is driven by an idea of doing existential elimination, but we also used universal elimination and existential introduction. So nice. This also highlights something useful. So the thing to note is, and I've mentioned this already, that a lot of times really to call these rules elimination rules are slightly disingenuous. Really they're derivation rules. So introduction rules always deliver a sentence featuring the relevant main operator. So if we have existential introduction, it always gives us an existential. If we have universal introduction, it always gives us a universal. If we have conditional introduction, it always gives us a conditional. When we have elimination, it doesn't necessarily mean that the sentence we're going to get out does not feature the same connective. As in this case, what we do is we derive an existential from an existential. But importantly, it's a different sentence, and we do so via the use of a particular arbitrary name. So good. Those are the key kind of rules here. If we really get universal introduction elimination and existential introduction elimination, you've pretty much got FOL natural introduction nailed. There are a few more rules, and we'll go through them quickly. So, the other kind of big block of rules, and these actually are fairly straightforward, are that we have quantifier conversion rules. So the quantifier conversion rules allow us to take certain kinds of sentences and flip them to other formats. So for example, if you have a sentence of the form that starts with a universal and then immediately has a negation, you can flip that and derive a sentence that starts with a negation and then immediately follows it with an existential. Or the other way around. If you have a sentence that starts with a negation and then immediately follows with an existential, you can flip the order here and get a universal followed by an existential. Similarly, if you have one that's got existential negation, you can derive negation universal, or if you have negation universal, you can derive existential negation. Now these rules really just let you flip around what quantifiers and negations you have and the order. This is useful. For example, if you have something like this, a sentence that starts with negation existential, you can pull a flip and then it's much easier to eliminate this universal. On the other hand, right, if you've got a sentence like this, well, maybe you want to generate a contradiction. So you're going to want to flip this around, get a negation in front, and then you can do some kind of contradiction. So again, these are really just sort of rules that help you figure stuff out as you go. They make your life a little bit easier when we're playing around with things. The last two rules have to do with identity. And the first one's straightforward. Well, actually, they're both pretty straightforward. So our first rule for identity, our identity introduction rule, is that nothing is required to show that something is identical to itself. In other words, at any point in time within a proof, you can introduce a self-identity. So if you want to, at any point in a proof, you can introduce that A equals A or E equals E. The only restriction is that you have to have the same name on both sides. And this is fairly straightforward, right? Because again, we don't need to show anything or prove anything to know that an object's self-identical. That's just given. Everything is itself. So that's identity introduction. The flip to identity introduction is identity elimination. And identity elimination is probably actually better understood as substitution. The idea here is that if we know that A is identical to B, then anything that's true of A is also true of B. In other words, for any sentence featuring the name A, you can replace it with the name B. You can replace all or just some of the instances of that name. So for example, if you know that A is B, you've got that somewhere on your proof line, and you have a sentence featuring A, you can use identity elimination, citing the identity and the relevant line, to then replace the occurrence of A with B. And the same way around. If you know A is B, and you have a sentence featuring B, then you can use identity elimination to replace B with your name A. So these are very handy because if you've got some claim about a particular object at a certain point, and you've got a claim about what looks like another object, but you know that they're identical, you can play swapsies and replace names. So that's the identity introduction and elimination rules. And more generally, that's all the rules for first-order natural deduction. We have universal introduction and elimination. We have existential introduction and elimination. We have the quantifier conversion rules, and we have identity introduction and elimination. That's it. The rest are the rules we import from TFL. Now again, I know that they're kind of funny, and they rely upon this idea about using an arbitrary name, which I hope has been kind of clarified a little bit. So what we'll do in the coming weeks is we'll talk more about these cases, we'll go through a bunch of examples, and try and make sense of how these rules work. My suggestion, if you've watched this lecture and it's still not quite clicking, go back and read the textbook again. I think it does a very nice job of kind of spelling it out. If you have questions or anything, you should always feel free. You can email me or message me about this stuff. And yeah, thank you guys very much. What we're going to do next week is we're going to talk a bit more about first-order natural deduction. So review this stuff. We'll talk a little bit more about our proof theoretic notions. and how these proof-theoretic notions relate back to some of the semantic notions that we talked about in the first half of the course. That'll be the plan. So thank you guys very much for coming. Take care, and I look forward to talking with you about this at some point soon.